All right. Well, hey, welcome to the second to last week, the penultimate week of class. Believe it or not, yeah, we're almost there. So we've got this week, and then next week we've got class on Monday and the final on Friday. So we are definitely in the home stretch. And we're also in the home stretch of the topics, right? We're in the middle of the final chapter, so that's looking good. But there are homework sets due tonight, so I want to go ahead and turn it over to you guys and see, are there any homework questions you'd like to talk about? All right, so we've got a whole bunch coming from 4.1. Let me just go ahead and write these down. So I've got 13 and 14, and then 11, 12, or 13. All right. So I'll put some question marks. How about next to the 11 and 12s, 13 ones? Yeah, and 4.2 I did move because we haven't talked about 4.2 yet. So, all right, and then Bruno looking at number 10. Adam from 3.7, number 14. All right. Okay, so it looks like we got a pretty good little selection here. So let me start with the section 3.7, and we'll go look at number 14. So I'll go ahead and share my screen here. Go see what these guys look like. So number 14. All right, so it says a function is a probability density function if it satisfies the following definition. That if you integrate from minus infinity to infinity, you get 1. Okay, I will tell you that there's a little bit more to that being a probability density function, but that's not really relevant right now. The function's got to be positive. Can't have a negative function. Anyway, so then it says the probability that a random variable lies between A and B is given by this formula. So basically how this works, if you're going to do probabilities, you have a function that describes your probability, and if you want to know what the probability is, you just integrate between those two values. So it's not really that big of a deal in terms of the general concept, but so the first one just says, determine which of the following is a probability density function. All right, so we'll go to the definition there. Let's look at the integral from minus infinity to infinity, and let's see if we get 1. So let me go ahead and write these functions down real quick. First things first, before we actually jump in there, notice that these are piecewise defined functions, meaning that what we use as our rule depends on what we're plugging in. And so for both of these, it's going to be 0 whenever we have numbers less than or equal to 0. And then after that, we use the other rule, either 1 over 6 plus x or 6e to the minus 6x. All right, so let's go see what we get. So we'll go back to the whiteboard. Let's clear all of that garbage. All right, so let's try the first one. Let's look at the first one, which was 1 over 6 plus x. All right, so what we're going to want to do, since we're doing minus infinity to infinity, I'm going to break this into 2 pieces since I've got 2 different rules. The first rule was when I was less than or equal to 0, and my function was 0. And then I'm going to add to that 0 to infinity, the integral of 1 over 6 plus x. So this is that classic trick we've used before, where if we want to integrate from A to B, you can cut it somewhere in the middle and then have the 2 different integrals that you're adding together. And that's what's going on here. All right, so this first integral is easy. I don't even have to worry about the infinity thing. This one's going to give me 0 because I'm integrating 0, right? What happens if I add up 0, even if it's an infinite amount of time? Well, it's 0. Now, the other one, we definitely need to worry about the infinity. So I'll write the limit as b goes to infinity of the integral from 0 to b of 1 over 6 plus x dx. All right, and so this one we actually have to do. Well, that's a pretty easy integral to do. That's just going to give us a natural log of x plus 6, evaluated at 0 and b. So we get the limit as b goes to infinity of natural log of b plus 6 minus the natural log of 6. All right, so here's the question. What happens to natural log of b plus 6 as b gets really big? Well, that is going to be infinity. You're absolutely right, Adam. This blows up. Because natural log just keeps growing. You look at the graph of that, it just keeps going up and up and up and up and up. So if that's infinite, that actually tells me that this diverges. But more importantly, I know this does not equal 1. So this is not a probability density function. All right, well, we could, I mean, at this point, because it was a multiple choice, we know that we're not going to click A. That just means we're going to click B. But let me show you that the other function actually does work. Okay, so you think the other one might be the same? Well, let's see. So same story. This time is going to be minus infinity to 0 of 0, but then plus 0 to infinity of 6 e to the minus 6x. So again, that guy's 0, no big deal. We'll do the limit. B goes to infinity of the integral from 0 to b. Okay, so now let's do this integral. So this one's going to be a u substitution. If you let u equal minus 6x, then du is minus 6 dx. So we already have the 6, so it's a minus e to the u, which is going to leave us a minus e to the u. So this ends up being minus e to the minus 6x, evaluated at 0 and b. So that's the limit as b goes to infinity of minus e to the minus 6b minus, let's see, minus e to the 0. So the e to the 0 is a minus 1, minus 1 is 1. So that's going to end up being a plus 1. This guy, think of that minus 6b. Let's rewrite it with a positive exponent, but in the denominator. So if we let b go to infinity, then this is going to be 1 over infinity. And what does 1 over infinity go to? Yeah, it goes to 0. Okay, so this ends up being 0 plus 1, right? So equals 0 plus 1, which is 1. So this guy definitely is a probability density function. All right.
Yeah, I don't know why. I took that as, I think somewhere I made a mistake and I was infinity plus 1 and it's 0 plus 1.
Yeah. And that could have been something as simple as a sign error, right? Like think about if when you did your integral, you didn't get a minus sign here. That could lead to infinity or something. But anyway, so that definitely works. So then for the last part where it said what was the probability, that's just a matter of putting in the bounds. It said what was the probability between 0 and 0.3. So if I want that probability, that's just going to be an integral from 0 to 0.3 of 6e to the minus 6x, which I think you see how easy that is. Just to we get the same antiderivative, we just plug in those numbers. So I'll leave that be a calculator exercise. All right, but it sounds like we're better for that one. All right, cool. All right, so let's go then look at the problems from 4.1, or at least some of those. Whoops, I don't want to go back into there. I want to go back here. All right, so 4.1. Let's go take a look at some of these. So I have a whole bunch on my list, starting with 10. So let's see what 10 has to do for us. Okay, so it says find the general solution to the differential equation y prime equals sine of x e to the cosine of x. All right, so first things first, general solution, what does that mean? How about let's just start with what's a solution to differential equation? Thanks, Alexi. The general is the where we have our c's in there. But when we talk about a solution, we're looking for a function that satisfies this differential equation. So that means we want a function whose derivative is sine of x e to the cosine of x. All right, so how are we going to do that? Oh, look at that. Alexi already beat me too. I didn't even ask the question. She already answered it. We're going to take an integral, right? We're going to anti-differentiate. So for number 10, it's just a matter of doing an antiderivative. And that's because y prime equals a function of x. Those are the differential equations you already know how to do really well. If we've got y prime equals something that's only x, all you got to do is integrate. So I don't think we have to go all the way through this one. But if you're going to try to integrate this, what are you going to do? Which technique? All right, so Bruno suggests by parts, because you see the multiplication, that could definitely work. That's not what I want to do. It's actually much easier if we do a u substitution. If you let u equal cosine, then du equals minus sine, and you notice we already have the sine times dx. So this is the same as the integral of minus e to the u du. So this is one of those cases where, yes, we've learned all these techniques, but don't overthink it. If there's an easier way, go for it. So I'm going to stop this one here because I know you know what to do at this point. But this one's definitely a U sub is where you want to go. All right. So let's go back and let's go look at 13, because I think 13 can cover our 11 or 12 or 13. All right, so this one says solve the initial or following initial value problems starting from y not equals 5. All right, so initial value problem. What does this do? What changes when we have an initial value problem? All right, thanks, Adam. Yep, we find the value of C. We actually calculate it now. The initial value is going to let us determine what that C is so that we go from a general solution to a particular solution. So we'll come back and we'll answer the second part in a minute, but let's do the first part. Let's find the y, but I want you to notice that this is the same kind of deal as y prime equals e to the 5t. We need a function whose derivative is e to the 5t. Well, that means we're going to integrate again. So let's go back to the whiteboard. So this time we've got y prime equals e to the 5t. So that means we're going to integrate e to the 5t dt. Again, a pretty simple u substitution. And that gives us 1/5 e to the 5t plus c. So there's our general, but now we're going to use the fact that we know that at 0, y is equal to 5. So we'll plug in 5 for y, 0 for t. So we get 5 equals 1/5 plus c, or c is equal to 24/5. So we can actually put that in, and now we have the particular solution. So this is the one of the very many that actually goes through the point 0, 5. So this is what's going to go into the first box. Y equals 1/5 e to the 5t plus 24/5. So given an initial value, just let you find your c. Now, if we go back, let's see what the second part of the question asks us to do. Okay, so then it says, at what time does y increase to 100 or drop to 1? All right, well, let's go back and look at this. So first of all, this one's not going to drop, right? Because it's an increasing function, e to the 5t. How did I get 24? That was 5 minus 1/5. Get a common denominator. It's 25/5 minus 1/5, which then gives me 24/5. Is that good, Bruno? Okay, cool. All right, so this one's not going to decrease. It's an increasing exponential. So it says, at what time does this increase to 100? Well, that just says, well, let y equal 100 and solve for t. So I would multiply everything by 5 to get rid of the fractions. So I have 500 equals e to the 5t plus 24. Subtract 24. 476 equals e to the 5t. Take a natural log. And then divide by 5. So for this one, it's going to be whatever the natural log of 476 divided by 5 is. I don't really care what the decimal is. Plus, your specific one probably has different numbers. But that's basically the idea for the second part. The fact that it said, when does it increase to 100 or decrease to 1? The decrease to 1 is going to happen if you have a negative power on that E, and I imagine some of these problems, when it randomly generates a value, sometimes those things are negative. All right, so good for number 13 there. So let's take a look at number 14 then. So here's the last one that people asked about, other than the other ors. So you throw a ball from ground level of mass 1 kilogram upward with a velocity of 28 meters per second on Mars, where the force of gravity is G equals minus 3.711 meters per second squared. All right, so approximate how long wording is really weird. Approximate how long the ball will be in the air on Mars. All right, so for this one, we need to go back to this. Actually, we don't even need differential equations because we've done this before. If we go back to the generic acceleration kind of stuff, so our acceleration is just gravity. So velocity is going to be the integral of acceleration. That's going to be the integral of gravity, which is G times T plus C. We saw before that C was our initial velocity. And then to get position, the position is the integral of velocity. So that's the integral of GT plus V naught, which is 1/2 GT squared plus V naught T plus C. And in that case, that C was the initial position. And I know I just really blew through that, but that's because we've seen this before. We've done this before. But what we're really doing is we're solving differential equations. Let me put it into the context of differential equations. We just solved x double prime equals G. So this is a second order differential equation, but it's an initial value problem because we know some things about it. Gets us this formula. So you've seen this formula before. It's going to be the same formula for on Mars as it was on Earth. The only thing that changes is G. So we also, though, need our initial conditions. So let's go back and see what it says. Right, so it says we throw a ball from ground level of mass 1 kilogram upward with velocity of V equals 28 meters per second with this gravity. So they just gave us numbers for everything. Obviously, you see the G, but that 28, that gives us V naught. This is our initial velocity. The from ground level gives us the X naught. What's the X naught if we're throwing it from ground level? That is 0, Alexi, you're right. The ground is 0. So let's go back and put that stuff in. So we'll go back to our whiteboard. Okay, so we've got X equals 1/2 times minus 3.711 plus 28t plus 0 855. I think I need one more 5. No, 1.855. One too many 5s. Whatever that is divided by 2. I don't care. I don't care. I don't care. Okay, I was right. Okay. Man, I still don't trust myself right now. Okay, cool. So there is our height given a time. So let's think about what they're asking us to do. The first one was, how long is it going to stay in the air? So that means I want to solve for t. And specifically, like you think about it, I toss this ball in the air, it's going to go up and then it's going to come back down. What I want to know is, when do I get back to x equals 0? So I'm going to let x equal 0. If I solve this for t, this is going to tell me, again, whatever that number is, this t, when we're at the ground. You're going to get 2 numbers. One of them is 0 because it was at the ground at the start. And the other is going to be when it lands. And that's going to be how long it's in the air. So that's the first part. I want to figure out how long it's going to be in the air. And this is the same no matter whether we're on Mars, whether we're on Earth, whether we're tossing it from the top of a building, whatever. If you want to know how long it's going to be in the air, you just wait until you see how long does it take for it to return to the ground, to x equals 0. The second part asks for how long until we reach, or not how long, but what maximum height we get. So I'm going to show you the calculus way of doing this. I want to reach the top of my curve. I want a maximum. Well, maximums occur where the derivative equals 0. So what I'm going to do is I'm going to set x prime equal to 0. Well, x prime is minus 3.711 t plus 28. So I set that equal to 0. This t is my t when I'm highest. Now that doesn't answer the question though, because the question was, how high does it get? Solving this equation just tells me when I'm at my highest point. So how am I going to get my highest point knowing this time? Actually, I'm not going to use the first derivative test. Adam, what that would tell me is that it is a maximum. But I already know it's going to be a maximum just because I know how balls fly in the air. Even though I've never been to Mars, I know it's going to be similar. All right, so then Bruno, you just said take the 28 divided by 3.7. Oh, that's going to tell me what this time is. But again, that's just getting me my time, not my location. Well, here's what I'm going to do. Whatever this t is, the 28 divided by 3.711, I'm just going to plug that back in here. Right? Because remember what this is giving me the height in terms of time. So if I know when I'm at my highest point, I can take that time, put it in here to get how high up I am. So that's the calculus way of doing this. There's actually a pre-calc way of doing this. Anybody see it? Think about what this point is. This is a parabola, right? Because of the negative t squared. So when I'm at the top, I'm actually at the vertex. This is actually the same as saying, what's the vertex of this? And so you can do the vertex thing, negative b over 2a. Yeah, no, maybe so. And so then the y is just f of t, whatever that number is. So you can actually get away with this without calculus, using your pre-calc tricks because it's a quadratic. But to be fair, this pre-calc trick actually comes from calculus. Take a look at, like, think about what Bruno put in the chat box for calculating the t, negative 28 over negative 3.711. That's negative b over 2a. So everything old is new again, as they say. Anyway, so hopefully that helps a little bit with this guy, but what you're seeing probably from 4.1 probably doesn't feel like you're doing anything new. At least it shouldn't feel like you're doing anything new, because you're not. You're doing things we've already done, because we've been solving differential equations. We just didn't call them that. And so that's kind of the point of this intro, is to be like, let's be real here. You've been doing this. You've already been doing it. You just don't know that you've been doing it. So, all right. Well, I see that we're actually way over time. I apologize, but I wanted to get to all of those homework questions. Obviously, the test review went a little bit longer than planned, but that's all good. All right. So just some things to remember. Homework's due tonight. There are just a couple of sections I did move forward. So make sure you get in and do those. The other thing I need to let you know is that this week I've got some all-day meetings that are going to happen on Wednesday and Friday, but I don't know exactly when all day. So I'm not sure if we'll actually have class or not. So you need to be paying attention to Canvas messages. I'll be putting them out there, letting you guys know. I'll post some stuff in there to let you know if we're actually going to meet or not. If we're not going to meet, like if I'm unavailable during class time, I'm still going to record lectures for the topics and put them up on YouTube. And again, I will share all this information. If and when it happens, I will share it through Canvas. So you'll get, always look at the messages in our class shell. But I will definitely still make videos so that you guys can watch them. And I will also let you know, if that happens, I'll add more office hours. I'll find more times that I'm available, so that after you've had a chance to watch them, if you still have questions, you can ask and come and find me. I think that's going to be better than trying to have a sub, especially since I'm not really sure if I'm going to miss class or not. Okay, so there is the possibility I might miss class Wednesday and or Friday, but I will let you know. I will definitely send out messages so everyone is aware, and I will let you know as soon as I know. All right, so if I find out in 5 minutes that that's the case, I'm going to put out a message and let you guys know as soon as I find out. Okay. So what would that mean for the quiz? That's a good question, Ayers, and I'm not really sure. Again, it's going to kind of depend on how everything plays out. That's one more thing that I will let you guys know about. It's possible that if we don't end up doing it on Friday, I might move it to Monday. I don't know. So, but I will definitely include that in my information to you guys once I kind of have a better idea of what's going on. All right. So I know it's kind of crappy timing, but at least we do have a chance to meet next week, so that we can still talk about stuff. All right. Anyway, so I think that's everything I've got. Anyone else have anything to add here at the end? All right. Well, then I will stop the recording and hope you guys have a great couple days. And I will hopefully see you on Wednesday.